Alright, so this video lecture is going to cover Chapter 3, which looks at 3 claims of scientific research and 4 important validities that are addressed in science. So what do you need to know from this lecture? The major things that I would like you to understand is how to differentiate between the 3 claims. So know what a frequency claim is and how that differs from an association claim and a causal claim. And then how to critically assess the 4 main validities. So that would be construct validity, statistical validity, internal, and external. There are certain validities that are most relevant for certain types of claims. And so I would want you to know, for example, an association claim, which validities are we concerned about? A causal claim, which validities are we concerned about? And the same thing for frequency. So before we jump into this, just a little coverage of a few topics. So variables. There are 2 types of variables. A variable can be either a measured or a manipulated variable, depending on how the researcher designs the study. So a measured variable is any variable where we are recording the values or levels as they naturally occur. So this could be something like I'm measuring how quickly a task is finished. It could be something like I'm measuring cortisol levels in somebody's bloodstream to determine something about stress. I could be measuring how long people sleep, how much they weigh, what type of brain activity they have, etc. So a measured variable is something where the researcher just goes in and measures something and gets the data. A manipulated variable is a variable that the researchers are interested in, so they think that this variable probably has some effect on some other variable. Vicodin has an effect on pain. Marijuana has an effect on nausea. How much you process information has an effect on how much you remember it. So a manipulated variable then would be where a researcher takes a variable and controls it, sets it at certain levels. So for example, an individual can get 4 milligrams of Vicodin, or 8 milligrams, or 10 milligrams. So the researcher then is manipulating the value of that variable. And then he assigns people to those conditions. So a manipulated variable can be anything. Similar variables as we had up above. So sleep, it's a measured variable if I just measure how much time people are sleeping. It's a manipulated variable if I assign people to either sleep 2 hours, 4 hours, or 8 hours. Now some variables can't be manipulated. So things like biological sex, drug use, brain damage, these can only be measured variables. I can't ethically say, okay, well, half of you are going to get brain damage and half of you aren't. Or half of you are going to have a sex change. There's some variables in the world that can't be manipulated. They can only be measured. Some other terms here. So a construct is a concept of interest. And so a construct can be something that's extremely concrete, like height, weight, or distance. But usually when the term construct is used, it's used in reference to more abstract concepts. Things like things that aren't readily things that you can't point to, weigh, or measure. They're not obviously out in the environment. So these are things that are more difficult to manipulate and more difficult to measure because they're abstract. So I can measure whether somebody is paying attention to something, like my lecture, for example, but there's nothing that I can point to and say, okay, that's attention. Same thing with love. So we know that, you feel that emotion that we call love, and some people, love other people more than others. So love changes. It's something that we feel, so we know that experience and that emotion exists. But it's how would you measure it? With an abstract construct, we also need something that goes along with it, which is called an operational definition. So this operational definition defines how the construct will be measured or manipulated. So for example, with attention, I could say, okay, well, since I can't, see attention, I can't know whether you're paying attention or not. But there are other things that I can look at, like if you're sleeping, if you're making eye contact, if you're nodding your head, if you answer a question correctly, and those things indicate you paying attention or not. So with an operational definition for something like stress, I can manipulate stress, and my operational definition then might be something like, you're going to give a talk in front of a class of 5 people or a class of 100 people. And presumably, the condition where you're giving a talk in front of more people will induce more stress. So that's a manipulated variable. Manipulation operational definition for a construct, stress. We could also have an operational definition for measuring stress. So I could measure stress by the number of your heartbeat, for example, or your cortisol levels, or whether you're sweating or not. If you're sweating and your heartbeat is up, then you're more stressed than somebody who isn't sweating as much and their heartbeat is down. So the operational definition gives us the specific way that we are going to measure or manipulate our construct. And that will be important in your papers later, when you are going to be telling me, okay, what is it that you're measuring, and how are you measuring that variable. So a claim is simply an argument one is trying to make. And in this case, we're talking about a researcher, or a person who is trying to gather objective information and present it to a group of people. And so there are 3 major claims. So we have frequency claims, association claims, and causal claims. So a frequency claim simply describes the rate or amount of one variable. Statements that are frequency claims might be something like 44% of Americans struggle to stay happy. So here we're looking at happiness is the variable, and the researcher probably just went out and asked people, are you happy or not? Or it might have been more sophisticated, but it's a single variable, and we're measuring this variable. 1 in 25 teens attempt suicide. Children's participation in sports has decreased 3% each year since 2011. So notice that these all have one variable. Happiness here is what we're measuring. In the second one, we're measuring attempted suicides. And in the third one, we're measuring participation in sports. A frequency claim is simply measuring one variable to see the rate at which that variable occurs. The second claim that we're going to talk about here is an association claim. And here we have 2 variables. And an association claim then describes the relationship between those 2 variables. And we have different types of association. We can have a positive association, a negative, I'm not going to talk about curvilinear, or no relationship, no association. So some examples here. Shy people are better at reading facial expressions. So here we have two variables, whether or how shy you are, or shy compared to not shy. And the second variable would be ability to read facial expressions. And so we would measure both of these. We're not manipulating any of those. So we're not making somebody more or less shy in this example. We're just measuring shyness, and then we're giving them different facial expressions in a test and asking them to correctly identify what those mean, and we're measuring that, their ability on that as well. Another example, people who multitask most are worst at it. So here we have people who are good or bad at multitasking, that's one variable, and then their performance on multitasking. So two variables, and we're measuring both of them, and we can then look to see, well, what is the relationship between those two variables. So here is a scatter plot, and scatter plots are often the way that association claims are presented visually to people, so that we can see the visual relationship between the two variables. So one of the variables will be on the x-axis and one will be on the y-axis. And so here we have the amount of abdominal fat an individual has and the number of dementia symptoms. So we might want to see whether those are related. And from the graph we can see that there's a general trend of moving from left to right and from bottom to top. So it's moving in this direction. And so what that would tell us then is that, one, this is a positive association, a positive relationship, because as the amount of abdominal fat increases, we find that the number of dementia symptoms in those individuals also increases. So as one increases, the other increases. That's a positive relationship. But a positive relationship, a positive association, also means that as abdominal fat decreases, the number of dementia symptoms decreases. So low on both of them over here, high on both of those variables over here. So a positive association, a positive relationship, simply means that both of the variables move in the same direction. They both increase or they both decrease. Now, contrasting that with a negative relationship, so here we see a trend where the data points are moving from the top left down towards the bottom right. And here we have two variables again, hours on the cell phone and sperm quality. So again, these are two variables that are measured. We want to see if there's a relationship between them. And we find that the more time spent on the phone, so cell phone time increases, we find a decrease in sperm quality. So a negative relationship means that the two variables move in a different direction. As the amount of time you spend on your phone increases, the sperm quality decreases. And as you spend less time on your phone, sperm quality increases. So low values of phone here, high values of sperm quality. Here we have low sperm quality, high hours on the cell phone. So they move in different directions. And finally, we get to a scatter plot of a relationship where there is no relationship between the two variables. So the duration of use of ADHD drugs and the frequency of other illicit drug use. So the idea is if you use prescription drugs, does that predispose you to experimenting with other types of drugs? And here the data would say no. And so we can look at this because there's no clear trend in a positive direction or a negative direction. It seems to be pretty spread out throughout the entire graph. So we have if an individual doesn't use ADHD drugs for very long, then they may not use drugs at all, or they may use a lot. And we also have some individuals here who have been using ADHD drugs for a long period of time, but they haven't experimented with other drugs, and others which have been using ADHD drugs for a long time and have experimented with other drug use. So there's really no relationship, because as this one increases, we find that this one is both high and low. So this variable, ADHD drug use, doesn't have a whole lot of influence on this other variable, the frequency of other drug use. Now we can use these associations to make predictions about the world. If we go here, to this one, which I showed, cell phone sperm quality, if we have a strong relationship between these two variables, then I can, with some amount of confidence, predict that if you're on your cell phone a lot, you're going to have lower sperm quality. In fact, I can even create some equation where I can say, well, if I take these data points here for someone who's been on the phone for 4 hours and find an average, then I can predict that if you use your cell phone for 4 hours a day, your sperm quality is going to be right about in here. And if you use it for 1 hour more, your sperm quality is going to be even lower, right about in here. So a strong association allows for strong predictions. This is why you take the SATs to get into college. Colleges know that kids who perform well on the SAT and have good GPA perform well in college most of the time. And kids who score poorly do poorly in college most of the time. So they can make predictions about who do we want to accept and who do we want to reject. If you score poorly on the SATs, they may predict that you're going to do poorly in school and not accept you into their school. Now that doesn't mean that you couldn't do well, and so these predictions are not 100% accurate, obviously. And the stronger the relationship we have, the stronger our prediction strength compared to a weak relationship. So here, in our no relationship example, which is right here, I can't really make a good prediction here because let's say you tell me that you have used ADHD drugs for say 12 years. Well, I don't know exactly where your average is going to be. It's going to be right about in here. But let's say you say that you've been using ADHD drugs for 6 years. Well, your average is going to be right about in the same place. So as your ADHD use increases, there's no change in the other variable. There's no predictable change in the other variable, and so my prediction would not be very strong. So the stronger the data points fit along a line, then the stronger the relationship and the stronger your prediction would be. And finally, that gets us to the causal claim. So causal claim describes how one variable, which is a manipulated variable, causes a change in a second variable, which is a measured variable. So just like an association claim, we have two variables in a causal claim. But here, instead of both of them being measured, like they were in the association claim, in a causal claim, one of them has to be manipulated. So some examples of causal claims could be that romantic music increases your chance of a date. So here we're saying that if you play romantic music when you're asking a girl out on a date, it will increase your chances of getting a date. So that's a causal claim. If you do this, it'll cause this change. It'll cause an increase in your chances. Flowers increase the perceived attractiveness of men. Here again, we're saying that if we give people flowers versus those who we don't give flowers, those individuals who get the flowers will be rated as more attractive by women than those who don't get the flowers. So those flowers are causing an increase in attractiveness. Now, how can we make such a strong claim that variable A is causing a change in variable B? And that is based on how we set up experiments. Experiments are the only method that allow us to make a causal claim. And the reason why is because causation requires three components. We need to satisfy covariance, temporal precedence, and internal validity. Now I'm just going to go over this briefly. Covariance is that we have to know that a change in variable A will lead to a change in variable V. So this one's pretty easy. If we change variable A and there's no change in variable B, then obviously A is not causing a change in B. We can go to a business aspect here. If you are decreasing the price of the product and that is not leading to an increase in the sales, then for whatever reason that decrease in price is not affecting the second variable of whether people buy it or not. So first we have to know that if I change this one variable, it should lead to some change in the second variable. If I don't have that, then I'll never have causation. And the second aspect that needs to be satisfied is temporal precedence. So here we have to know that the changes in one variable come first and then produce changes in the second variable. So what happens is we need to manipulate and create a difference and then measure something rather than the other way around. So an example here would be, does yoga increase happiness? Just an example. And so let's say you go out and you go to a yoga class and you measure, you ask people to rate their happiness on a scale of 1 to 10, 10 being very happy. And then you go around to people that are walking on the street, the general population, and you ask them to rate how happy they are. And you find that the people in the yoga class, when you take the average of their responses, report higher happiness than people walking on the street. And so you conclude that going to a yoga class will increase your happiness. Okay, now this would be a false conclusion because we don't have temporal precedence satisfied yet. And so the critique of that study is that we don't know whether happiness came first or yoga came first. And that's because we didn't manipulate a variable. So it could be that happy people go to yoga. And yoga doesn't cause an increase in happiness. Those people were already happy and that's why they're in the yoga class. Or it could be that yoga causes happiness. And these individuals have been going to yoga and now that's why they're happier compared to the people walking on the street. The problem is, based on the way that I designed the study, I don't know what the answer is. I don't know if happiness came first or if yoga came first. So in order to get around temporal precedence, we have to manipulate one variable. This is called the independent variable. Then, if I manipulate it first, so I put people in a yoga class, or I put people in a CrossFit class, and then I have them do that class for a while, so I know that they're going to yoga first, or they're going to the CrossFit class first, and then I measure their happiness afterwards, then I know that variable A came first. I know that yoga came first, and then I'm measuring happiness. So we get to the third component of causation, which is internal validity. And this is the step where researchers are trying to make sure that there aren't any other explanations for the result. So in an experiment, to get causation, we need to know that the variable that I'm manipulating comes first, and then I measure something after that. And 2, the only thing that changes in my experiment is that manipulated variable, and all the other variables are the same. And if that's the case, then if there's a change in my second variable, that the only thing that can create that change is my independent variable. So here's an example. If I am wondering whether students who drink caffeine during an exam or right before an exam, if that helps them do well on the exam. So I can design the study where I think that coffee is affecting exam performance. So I have 2 variables, exam performance and caffeine. Now, importantly, I'm going to manipulate whether people get caffeine or not. So in one group, I'm going to give people a decaf coffee, 16 ounces, and in another group, I'm going to give people 16-ounce regular coffee. And then, after they've drank the coffee, so the coffee or no coffee comes first, then I'm going to give them the exam, same exam for both groups, same number of questions, they're going to take it in the same class, same time of day, and then I'm going to measure their score, how well they did on the exam. So the independent variable, what I'm manipulating is whether they get coffee or decaf, and what I'm measuring is the dependent variable, and that's the score on the exam. So then I make sure that everything about the exam is exactly the same. The way that I score it, how much time I give them, what color paper it's on, they take it in the same room, same time, same day, same number of questions, exact same questions, etc., etc., etc. So everything's the same. The only thing that's different between the 2 groups is whether they got coffee or decaf. Now, the second important point is that I have to randomly assign people to the groups. So by doing this, if I randomly assign people to these 2 groups, so let's say I put 500 people in the caffeine group and 500 people in the no caffeine group, decaf. Since I'm randomly selecting people, there should be an equal amount of really smart people in the decaf group and really smart people in the coffee group, and an equal number of not so smart people in the coffee group and not so smart people in the decaf group. I should have relatively equal numbers of men and women in both groups. I should have sleepy people in both groups. I should have people who, just ate a really full meal. I should have equal number of, fathers and mothers in both groups. I should have ethnicity pretty evenly distributed across the groups. So because I'm randomly assigning participants, the randomization process means that these personal characteristics should even out across the 2 groups. So all variables are the same across these 2 groups, except one group gets coffee, one group gets caffeine. Decaf. And so if I find that the caffeine group has higher test scores, the only thing that can explain why they have higher test scores, it can't be intelligence, because intelligent people are in both groups. It can't be whether you're tired or not, because tired people are in both groups. The only thing that's different is whether you got coffee or not. And that's why we can say, with this type of design, that the caffeine causes an improvement in your test scores, because there's nothing else that could explain it. So the experiment is the only method which allows for causal claims, and that's because we manipulate the independent variable, measure the dependent variable, randomly assign participants to groups, and keep all other variables constant across those groups. Okay, so now we get to the portion of the chapter that deals with the 4 validities. So validity is just the appropriateness of a conclusion. So something would be valid if we make a correct conclusion. And so in research, we want to assess whether we are making appropriate conclusions in 4 specific areas. So we have construct validity, external validity, statistical validity, and internal validity. So I'll go over these now. So first, construct validity. So construct validity is how or where we assess the quality of the operational definitions. So remember, the operational definition is how we measure a variable or how we manipulate the variable. So it's the way that the researcher manipulates a variable or measures a variable. Remember, there are many ways to manipulate a variable. If I'm looking at something like hunger, I can feed you vegetables, or I can feed you fruits, or I can feed you 10,000 calories or 5,000 calories. So with this variable of food, I can manipulate it in many different ways. And so when we're assessing construct validity, we want to see, well, is the way that the researcher manipulates the variable a good way? And is the way that they're measuring the variable a good way to measure the variable? So an example would be something like, okay, like let's say we're trying to get information about how often people drink and drive. And we then do a self-report. So we just walk into a college and start pulling people aside and asking them, do you drink and drive? So is that a good way of measuring drunk driving? No, not really, because people are probably going to lie. And so a slightly better way of measuring that might be an anonymous survey. So we pass out flyers at campus and ask people to just say yes and how many times and how frequently have they drank and drive, but they don't put any information on it. So people are going to be more honest because that information can't be traced back to them. But still, people may not fill out the surveys, or they may lie still. And so a better way would you just watch people. So you set up a checkpoint, you don't pull anyone over, and you just measure signs of drunken driving. Or if you have the ability, you stop everyone and you measure them, and maybe you don't arrest them, or maybe you do if you're the police. But that would give you a better idea of how many people are drinking and driving than just asking them. Another example, this one for manipulation. So let's say I want to determine whether different types of music have an influence on your mood. And so let's say I choose Mozart to relax people, and I choose Dragon Force to induce agitation in people. So then, if you're assessing construct validity, you might be saying, okay, is that a good manipulation? Is Mozart a good a good artist to make people feel relaxed? And is Dragon Force a good band to play to people to induce agitation? And hopefully your response is, well, maybe. Some people might become very relaxed to Mozart. Some may not like Mozart. Some people might actually find Dragon Force relaxing, and other people might find it agitating. So here, if we're looking at mood and memory, or music and mood, we would want to assess, okay, is there a better way of producing relaxation, and is there a better way of producing agitation? And the answer would probably be yes. So the second validity is external validity, and this is we critique the samples that are used in our tests, in our research, and critique whether the information that we get about that sample does it generalize to the population that we're interested in? And does it generalize to other situations that we're interested in? So as scientists, we can't study everyone, and so we take a sample. And the question is, do we gather the sample in a way that makes it so that we can conclude the results from that sample are probably also true for the population, or not, if we choose a poor sample. So here's an example. So let's say somebody is interested in whether marijuana will be legalized in California. And so they gather a sample of college students and ask them questions, and then they report the results back to the board or people that are interested and say, yes, this bill is probably going to pass. Well, the issue there is, so is that a good sample? Is that sample representative of all people in California? And the answer is no. It's representative of college students, but college students don't represent all Californians. A better way to gather a better sample that would allow better conclusions about whether the bill will pass in California is you randomly select people all across the state in all different professions, all different ages and ethnicities and gender. Okay. So the third validity is statistical validity. And this one is assessing whether we did the statistics correctly or not. So there are two issues here. One, we could claim, so we have a type 1 error that could occur. So we run a study and we say caffeine improves exam scores. And so there are two possible errors. The first error is a false positive. So this would be where I claim an effect. So I claim that caffeine improves exam scores, but that effect actually doesn't exist. It only existed because of the specific sample that I used. So it's an anomaly. If I were to run this test again, maybe I don't find those results. That would be a false positive. False positive saying, I say as a researcher, hey, there's this really cool effect, caffeine improves exam scores, but actually I'm wrong because I got that result just due to chance. The second possible error when making a conclusion is that I, as a researcher, think that caffeine will improve exam scores, but the data that I get says that it doesn't. People that got decaf and got caffeine showed similar exam scores. So here, this is called a type 2 error, which doesn't really help, or it's a miss. So I'm saying, hey, actually, there is no relationship here. A doesn't cause B, but I'm actually wrong. It does. I just didn't find it. So a miss is where I claim there's no effect. Caffeine doesn't improve exam scores above and beyond decaf, but actually there is an effect, and I didn't find it for whatever reason. I didn't. You make the test difficult enough, or I messed up on how I scored it. I made a mistake, or whatever. There are a bunch of different reasons why that could happen. So we would be critiquing statistical validity when we're looking at these things. So we'll talk more about statistics later in the course. So I'm just going to jump ahead here. Finally, we get to internal validity, and so this is a critique of whether there are alternative explanations other than the explanation that I'm claiming as the researcher. And so this is looking at, are there confounds in the study, and how well does the study control for these extraneous variables? So remember, a confound is an uncontrolled variable that changes with the independent variable and can explain a change in the dependent variable. So what does that mean? That means that as a researcher, I say caffeine improves exam scores. A confound would be some other variable that is also systematically different. We talk about confounds more later. And it also explains the results. So a confound is basically something where I don't know what the right conclusion is because it could be the confound that's explaining it, or it could be my independent variable. A confound in the coffee study would be if I designed it poorly, and let's say instead of randomly assigning people to the two groups, I instead ask everyone in the front row to be in the coffee group and everyone in the back rows to be in the decaf group. And then I find that those people in the caffeine group did better on the exam. Now, I don't know whether it's caffeine, which caused those increase in exam scores, or maybe there's something about people who sit in the front row that made them do better. Maybe they're just more motivated than people that sit in the back. That's why they got there early. And it's motivation which made them perform better, and caffeine has nothing to do with it. So that motivation would be a confound. I don't know whether it's motivation or caffeine which caused the scores. So when we're assessing internal validity, we want to see, well, is there something else that's possibly going on? So an example here, there was a study that found, it looked at women and nutrition, and it found that women who took vitamins more often were more likely to die younger than women who didn't take vitamins as often. Now, this is not a causal statement because we didn't manipulate anything. We didn't randomly assign women to either take vitamins or not. We just measured. We asked them, how many vitamins do you take? What do you take? And then we measured when they died. And we found a relationship. But it doesn't mean that vitamins cause you to die younger. In fact, what it probably represents is some other third variable. It's possible that women took more vitamins who were sickly, and the sickness killed them early, or they were smokers. They tried to counterbalance their, that bad behavior with a positive behavior, taking vitamins, but eventually smoking killed them. So when we're looking at these types of issues, we want to see, is there some other way to explain it? Here's one more. Adolescents who report consistent marijuana use show less interest in school and after-school activities. Does that mean that marijuana causes adolescents to perform poorly in school? Maybe. It's hard to know because we can't, again, ethically, randomly take kids, assign them to two groups, so that all their personality characteristics are even in those two groups. I can't do that ethically and then say, okay, you're going to smoke marijuana and you're not. And marijuana may make you dumb, and sorry, it's for science, I have to put you in that condition. We can't do that. So it's possible that adolescents smoke marijuana and marijuana makes them not care about school as much. Or it's possible those kids didn't care about school and that's why they're not in school and they're smoking marijuana. So we don't know what's happening there. So we have some confounds. Now, when we are assessing frequency claims, we really only are looking at construct validity and external validity. So does our sample apply to the population, and is it measured well? We don't care about statistical validity because it's just a frequency. It's how many people said yes in the total number of people we asked. An association claim adds that construct, adds the statistical aspect because we have to run some stats on the data that we get to determine how strong the relationship is and what type of relationship. And finally, with the causal claim, we need internal validity because we need to assess, are there other confounds, other variables, which could cause the results that I found that aren't the one I'm interested in. Remember, with an association claim, we can't make a causal claim, so we're not worried about whether there's internal validity or not. All right, that's it for this.